Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This subject is the first paper in the first semester. This lecture is the 53rd lecture in the series. In this part of the lectures, we are dealing with digital electronics. In the last lecture, we have learnt some of the logical expressions or logical operations, followed by the three basic logic gates, namely OR gate, AND gate, and NOT gate. Towards the end of last lecture, we saw there are some combinational gates available. In this lecture, in continuation to that, we are going to learn about some combinational gates. So, let us see today's session outline before we actually start this lecture. In this session, we are going to see the combinational gates. Two gates we are going to learn. One is NOR gate, the other one is a NOT gate, and we are going to have a reason why the NOR gate and NAND gate are called as universal gates, and also some of the gate ICs, integrated circuits, having gate embedded in them. All these we are going to learn in this lecture. What are combinational gates? The three basic gates, standalone gates, we have learnt in the last lecture: OR, AND, and NOT. We have first understood the logical meaning of these operations, and then the circuits involving these operations called gates also we have learnt. For various inputs, how do we get the output? In the form of truth table, we learnt the gates. Also, we had an analogy of these gate operations with a typical electrical circuit in which the switches are used to mention whether the gate is or the circuit is on or off. We had a bulb connected in the circuit. If the bulb glows, that was considered as an on state, or its logical equivalent is 1, and if the bulb does not glow, then that was called off state and its logical meaning was 0. Now, when we combine the gates, what are the gates possibly we will get? We will have a look at the combinational gates now. We will start with a gate called NOR gate. What is NOR gate? Let us see what it is. Before that, we will recapitulate what are the logical operations. An operation that acts on binary numbers to produce a result according to the laws of Boolean logic is called logical operation. Boolean logic is a form of algebra in which all values are reduced to either true or false. Here the meaning of true is 1 and false means it is 0. The zeros and ones and their meaning we learnt in binary number system. So, we are well equipped to handle the Boolean algebra. There is a separate session we are going to have later, in which how do we use the Boolean algebra to simplify expressions, that we will learn elaborately. But right now, the combinational gate. Logic gate is an elementary building block of a digital circuit. At any given moment, every terminal is one of the two binary conditions, low or high. The low meaning is 0 and high meaning is 1, represented by different voltage levels based on the circuit that we use. The basic logic gates are already covered. Let's anyway have a quick recap of what are the basic logic gates. The basic elements that make up a digital system are OR, AND and NOT gates. We will see the other combinational gates like NOR and NAND gate in this lecture. All the possible inputs and outputs of a logic circuit are represented in a table called truth table. NOR gate. This is a NOT OR gate. The short form that is called as NOR. Its meaning is not OR. It can be made out of an OR gate by connecting a NOT gate at its output. The Boolean expression to represent NOR operation is given by this logical expression, which has the y as the output is equal to a plus b the whole bar. A plus b is the OR operation. When we have a bar for the whole a plus b, or it is also called the complement of a plus b, then it is a NOR operation. The first operation here is the OR, that we have to keep in mind, and then its complement is taken. So, that is called a NOR operation. Though when we call the gate or the operation as NOR, not OR, actually the OR operation is performed first, followed by the NOT. So, let us see the circuit diagram representing a NOR gate. This is the truth table for a NOR gate. It is the complement of the OR gate. So, for the various input combinations, we have the output here. It is the complement of the OR gate. If you want some sort of clarity in the output, we can introduce one more column here and write what is the OR operation, what is the output of OR operation, and then its complement we can take. But here the NOR output is directly given, and the circuit symbol would either be like this with two gates, a NOR gate followed by a NOT gate. In the output of an OR gate, we have to connect a NOT gate, or these two can be combined together, and as a single gate also we can represent the NOR gate. The OR gate, which has a bubble at the output, is representing a NOR gate. So, this is the NOR operation. This operation is also a directly taken operation, as like the other three gates. This gate will be very much useful in simplifying logical expressions involving the Boolean algebra. Now, let us see one more gate, that is called the NAND gate. Its operation is also similar to the NOR operation, except for the OR part. Instead of the OR, we have here the AND. So, it is a combination of AND gate and a NOT gate. Let us see what it is. This is a NOT AND gate. It can be made out of an AND gate by connecting a NOT gate at its output. The Boolean expression to represent this NAND operation is this. We have the y as the output, which is equal to a dot b and its complement. A dot b is the AND operation, and the whole complement represents the NOT operation done at the output, of an AND operation. So, we have this as the output A dot B the whole bar. Customarily, the dot is normally not represented in Boolean algebra. We do not actually represent this dot, it is simply written as AB. AB is the AND operation. Normally, for the AND operation, we put a dot A dot B, but for lengthy expressions and all that, for reasons of nothing, it is just dropped. It is simply written as AB as the AND operation. We have to call that as A and B, but it is not represented with the dot. This point we have to note at this juncture. Hereafter, we will not normally use the dot in the output of AND or the NOT NAND operations. Now, the two combinational gates we have learnt, namely NOR gate and NAND gate. Now, the NAND gate, how it is represented, the truth table of that. This is a truth table for the NAND operation. Again, for the various input combinations for a 2 input NAND gate, the output are given here. This is the complement of the AND gate. When we compare these outputs with the AND operation, we will be able to understand this is nothing but the complement of the AND. And as we have done in the NOR gate, here also the two gates could be used for representing a NAND operation and followed by a NOT. But if as a single element, if you want to use this in the circuit, we can typically use a NAND gate symbol with a bubble at the output. So, this is the NAND gate symbol, which is very much used in electronic circuits. Now, what is the reason for learning the NAND and NOR operations? Is there any importance attached to these gates? Definitely, these two gates are very important. When we take up the Boolean expressions, the NAND and NOR play a major role in implementing some of the logical circuits. Now, NOR and NAND as universal gates. NOR and NAND gates are called as universal gates because using NOR and NAND gates, all other gates can be designed. Hence, they are also called universal building blocks. Let us see how the NOR and NAND gates are used to design other gates. Before that, the reason for calling them as universal gates. These two gates are sufficient for us to design all other logic gates like NOT gate, OR gate and AND gate and other logical gates. So, that is why these two gates are called universal building blocks. Before we actually learn about the designing of other gates with the NOR gate and NAND gate, let us take a short break and then come back to see what are the possible circuits that we can design using these two gates. Welcome back. We have learnt about the reason for calling NOR gate and NAND gate as universal gates. Now, to prove this statement, now it is time for us to design the other gates. What are the basic gates? The gates like OR gate, AND gate and NOT gate using the NOR and NAND. So, let us see how the circuits are designed for the other gates. Let us now take up for our discussion the NOR gate as universal gate. What we should show? We should show the NOR gate is used for designing the other basic logic gates. So, let us have a look at the circuits. NOR as universal gate. The first circuit shows the NOR as a NOT gate. For a NOT gate, we need only one input, but the basic OR and NOR NOT gates which we have seen so far had two inputs. So, to convert a NOR gate into a NOT gate, we need to tie the two inputs of a NOR gate and then use it as a single circuit element. So, in that case, the complement of the input is obtained as the output. So, that is the meaning of this NOR gate getting converted into a NOT gate. Similarly, these are just the schematic diagrams. Actually, how these gates are acting as the typical NOR NOT gates, we will learn elaborately with the circuit elements like diode, transistor, resistor. So, that concept is reserved for the upcoming lectures. In this lecture, we are just looking at the basic circuit representations, how a typically a logic gate functions. We are not yet familiar to that, we are not yet learned it. So, in the future lectures, we will learn about them, but here we get an idea of the circuit element, how the logical operation is performed with the help of just the symbol representations. Now, let us see how the NOR gate is used for the design of OR gate. It is a very clever design. When we have NOR operation, if you want to convert the NOR into OR, once again we need to take the complement, because the NOR itself is the complement of OR. One more time when we take the complement, then we will get the OR. So, we can use a NOR gate along with a NOT gate. The NOT gate derived from the NOR gate. Just now we have seen we can design a OR gate. Let us see how it is done. So, this is how the two gates are used. A NOR gate, for this NOR gate, the output will be A plus B the whole complement. So, one more time when we take the complement of this using a NOT gate, which is converted into a NOT gate from a NOR gate, that is shown in the previous symbol, then we get a OR gate. Now, the same NOR gates could be used for the design of AND gate. For this purpose, what do? We complement the inputs first. The A is complemented using a NOT gate and again B is complemented. So, it is the complements given here as the inputs and the output would be AND operation. Similarly, a NOR gate, all NOR gates here can be used to design a NAND gate. Because we have designed a AND gate, one more time we need to take the complement of this to get a NAND operation. Especially for these simplifications, we need to use the logical expressions. We should also learn about some of the logical expressions, how the logical expressions are simplified. We have to learn the way in which the expressions are simplified. For that, the theorems available, that also we need to learn. So, a separate lecture is devoted to give the basic understanding of simplification of logical expressions using the theorems called De Morgan's theorem. So, a separate lecture is devoted for understanding the circuit simplification or the logical expression simplification. At that time, we will understand how the complemented inputs given to a NOR gate gives us the AND operation. So, we will have to wait till that topic is covered. At that point, we will be able to understand how this AND operation is possible with the NOR gates. So, here we have got the basic idea of designing the other gates using NOR gates. The same way we can use the NAND gates also to design the other gates. So let us continue to see how the NAND gates are used for the designing of the basic gates like NOT, OR, AND and NOR, etc. So let us have a look at the circuit. NAND as universal gate. The same way how NOR was used as a NOT gate, we can use the NAND gate also as a NOT gate. Again, we need to tie the two inputs together, and when we give A as the input, A complement is taken as the output and vice versa. So, in this NOT operation, both the NOR gate and NAND gate behave in the same manner, just the complement is taken. Now, the NAND gate as AND gate, already it is a NAND gate, so it will give the NAND output. If it is complemented one more time using a NOT operation, we get the AND operation. So, it is a simple representation given here. NAND gate could be easily converted into a AND gate. For that, we need to use two NAND gates. Here, a NAND gate as a OR gate. Again, the complemented inputs are to be given to this NAND gate to get a OR operation. To complement the inputs, we are using the NOT gates derived from the NAND gates. And again, if this OR operation is complemented, we will be able to get a NOR gate. So, it is well understood here by this circuit. One additional part is connected to this OR operation. Just for complementing the OR, we are using one more NOT to get the NOR operation. So, that is why NOR and NAND gates are called as universal gates. We can design all the other gates using only either the OR gate, NOR gate or the NAND gate. Especially when we use the NAND gates, the circuit designing will be very easy. So, that is why the NAND gate is especially called as universal building block. The NOR operations involve some sort of tedious circuit designs, but when we use NAND, implementing any logical circuit into the design expressions will be very easy. So, the NAND logic is very much preferable over the NOR, but nevertheless both the gates are called as universal gates because using them we can design all other gates. Where these gates are available for commercial purpose, do we have to design every time all the connections and all that? It is available in the form of integrated circuits. They are called IC chips. So, in the IC chips, these gates are already designed or embedded. All we need to do is identify the respective terminals for inputs and the outputs, and accordingly we can use these gates which are readily available. What are integrated circuits or simply called as ICs? So, let us see how these ICs are used to hold these gates embedded in them. So, it is time for us to get the basic points about the ICs, especially the gate ICs. So, let us see what they are. Integrated circuits. An integrated circuit referred to as an IC or a chip or a microchip is a set of electronic circuits on one small plate called a chip of semiconductor material, normally silicon. The IC design itself is a very great field and the technology involved is something very huge. But at this point we need to keep this point in mind. It is possible to design lots of the electronic circuits in a single chip called integrated circuit. These circuits are available commercially, in which the gates are already embedded. We can have a look at the ICs with the terminals. Let's have a look at the ICs, how they look like. This is how the IC chips, especially the circuits, would look like. I have not shown the commercial picture of the ICs, but a typical IC chip in which the gates designed are only shown. In the future lectures, I would like to show how the IC chips function. But right now, I wanted to show how the gates are embedded in the ICs. Let's take for example an IC called IC 7404, which is holding 6 NOT gates in it. Any gate IC of the series 7400, that is called the gate series ICs, will have 14 legs or 14 pins available in the circuit. The 14th pin is used for giving the power VCC. Normally they operate with a voltage of 5 volt, and the 7th pin is used for giving the connection, that is the ground connection. 7th pin is devoted for it, and this circuit we have to keep in mind. Pin 1 is the input, pin 2 is the output for a NOT gate, 3 is the input, 4 is the output, like that. We should not, because these components we cannot see from outside, they are all kept inside, designed inside. So the pins and the configurations we should learn. And similarly, I would like to show one more gate. Take for example the OR operation. The gate is IC 7432, which holds 4 OR gates. 1 and 2 are the inputs and 3 is the output. 4 and 5 are the input for another gate and 7 is the output, and it goes like that. Here also these pins we should keep in mind. Like that, there are several gates. An IC chip is there for holding the NAND gate and then NOR gate, etc. For each IC chip, the pin configuration is important. Invariably for all the gates, pin 14 is VCC and pin 7 is the ground. This point we can keep in mind, that is uniformly allotted for all the gates. We have 3 input gates also. 3 inputs and 1 output gate also are available in the form of integrated circuits. In one of the forthcoming lectures, I would like to show how typically an IC chip would look like with the pins. The external part of the IC I would like to show. So we have learnt about the combinational gates and how gates are embedded in circuits called integrated circuits in this lecture. So let us see the session summary for today's lecture. In this session, we have seen the combinational gates, NOR gate, NAND gate, and why NOR and NAND are called universal gates, and also some of the gate ICs. It's time for us to test our understanding by answering these questions. What are combinational gates? Explain the logical operations NOR and NAND with truth tables. Why are NOR and NAND gates called universal gates? Give the circuit design of other gates with NOR and NAND gates. So with this I would like to conclude today's lecture. We will see about the other special gates and the inputs about the IC circuits in the forthcoming lectures. Thank you.